I've done videos in the past on how to create a dual-sided power supply, positive and negative voltage, from a single rail power supply. And I will do more of these videos in the future. But so far, I've involved transformers and sine wave filtering and all this other stuff. There's another trick you can use. It's a trick that only works for signals, not power. So you're not using it to power an amplifier with negative voltage. It uses the same technique as the videos I've done about voltage doubling, where you can take a single rail and increase that voltage all you want, not for power, but for signal. You can use that technique to do a voltage reversal. So instead of adding voltage, you're flipping it around. You have a single rail power supply. The goal is to take that power supply and add a negative rail that's the same voltage. It won't be because there will be diode drops like usual, but that can be mitigated so you can get, with good diodes, you can get very close to the same negative rail as you have a positive rail. If your positive rail is not big enough to make the negative rail you need, then just use voltage doublers to increase the positive rail and then make the negative rail. It works fine. Just like before, you need a square wave. So here's your square wave. Now the square wave is going to need to be the voltage that you want your negative rail to be. The negative rail thing I'm going to do, I have tried to stack it like you can stack the voltage doublers. I haven't figured out a way. If you know of a way, let me know. But I can only get it working as a single stage, so the square wave has to be the proper voltage. Now, I did a video recently on how to take a lower voltage square wave and drive a higher voltage square wave with it. So you can use that technique if you need. So for now, let's assume that this square wave is the full supply voltage. We need the usual 2 diodes and 2 capacitors. And there it is, simple as can be. 2 diodes, 2 capacitors, just like the doubler. So at the beginning, let's assume that the square wave is low. So we've got 0 voltage, 0 voltage, 0 voltage, nothing happening, everything discharged, cool. So now the square wave goes high. So the square wave is putting out like this. This capacitor is charging this way because this diode is letting the voltage back through to ground and the square wave. But the same is not happening here. If you got 0 volts here, you're going to have a diode drop here, 0.5, 0.7. Let's just say 0.5, because that's about what my diodes have been doing. So in order for this diode to conduct, you'd have to have, 1 volt or so here, but there's nothing happening to make that volt. So this just blocks the current over here, and the only thing that's happening is charging through this. So the capacitor charges up to the square wave supply, whatever that voltage is, whether it's your rail or the output of a doubler with the push-pull, whatever. But it charges to the square wave high, minus this diode drop, of course. So just like the doublers, if you have better diodes with lower drops, you'll get a higher maximum voltage. Now the capacitor is charging this way, so the positive charge is accumulating on that side. So if you use an electrolytic, you put it that way. You always put the electrolytic so that the positive charge enters from positive to negative and leaves from negative to positive, the same orientation you'd have any power source. If ceramic, of course, you wouldn't have to worry about. So now this capacitor is charged through this diode, and the square wave has gone low again. Conceptually, not actually, but conceptually, this square wave here is basically just a short to ground. So this is just a wire right here. So I can draw that conceptual wire like this. It's a common thing that's not intuitive when you're learning electronics. People think of ground as the end. I've even had a comment that somebody's eyes were opened because of the way I explained ground and something went through ground. Ground is just another wire with a particular voltage. It's not the end. Always think in terms of circuits, not drops. But anyway, this capacitor begins to discharge this way. So it's trying to push out through ground and pull in its back end. You always have to have current out and current in be the same. So if it's going to push out this end, it has to pull in from the other end somehow. Well, it can't do it through this diode because it's the wrong way, so this diode is blocking. But it can go over here. Aha, we have a capacitor and a diode facing that way. Let's take that off. So the current is going down this conceptual wire. It's charging this capacitor, and once again, if you use an electrolytic, you put it this way because you're charging in this way. The charging current, you're pushing it in, accumulating on the positive end. And that's going through this diode back into that capacitor, discharging. But we have a parallel path. It's also going through the load at the same time, nothing stopping it. So the load is going to see the high of the square wave minus the diode drop. However, here's ground. The current is coming from ground. It's negative. The load is seeing a negative current, negative voltage. So there you go, there's that rail. And this capacitor is being charged up again, pointing down, and then eventually the square wave switches back to high. So it's not going through that conceptual load anymore. It's charging the capacitor back up. So this path is gone. It's charging back through this diode up this way. But the same as before, this diode is going to block it, so this charging is not going to go through this part of the circuit. What is, however, is this capacitor that was charged up. Positive end was charged up, so it's going to push it back down. If it's pushing out this end, it has to be pulling in this end in order to discharge. That's how a capacitor works. Well, this diode is not going to let current go that way, even though it could push current around through here and through the capacitor and diode. There's no way for that current to get to its back end. And it's not going to send it in a circle. That's not how electronics works. So since there's no way for current to come through this way into the capacitor, it's not going to go out that way either. So it has to come from the only other way it can, through the load. So the capacitor discharges down through the ground connection, up through the load from ground and back around to the capacitor. Once again, the load is seeing a negative current, which means a negative voltage. And that's how it works. The voltage doublers would charge a capacitor and then would push against the capacitor and add the capacitor to the supply, and then they would use that to charge a supply capacitor so that when the square wave switched and they had to recharge that capacitor, the other capacitor was supplying the load in the meantime. So the load capacitor was charged and supplied by the power capacitor, and then when the power capacitor was charging, the load capacitor would keep it going until it started getting charged again. And the same way here. When this load capacitor is being charged, this supply capacitor is supplying the load. And then this supply capacitor will recharge the load capacitor while supplying the load. So each half wave, the load is being fed by one or the other capacitor. And each half wave, one or the other capacitor is charging. And once again, this is why it's not meant to drive a high current load, because if you draw too much current from the capacitor, the voltage is going to drop. So the more of a load you drive, the less voltage you're actually going to get. It's going to shrink your negative rail, and you're going to see noise in the form of the charging-discharging cycle. You can mitigate that by adding capacitance. More capacitance means you can drive a bigger load, but you have to actually feed that capacitance. So if you add too much capacitance to the load, you're going to cut the voltage anyway because you're not going to be able to get enough power from this into it. So you've got to balance it. But that's it. That's the negative rail. Stick to transformers for power. But this is great for signal. So you can take something as simple and basic as a 5-volt Arduino. Single rail 5 volts. You can increase that voltage, and you can add a negative rail, and you can feed comparators or other elements of the circuit as long as they don't draw a lot of power. If all you need is signal, you could have hundreds of volts flying around in a 5-volt Arduino, should you want. But that's a topic for another time. For now, let me just show you it in action. So I have here the same setup I've been using for my voltage doubler videos. A 5-volt supply and a 555 timer providing a square wave, push-pull amplified to supply the rest of the system, and then I'm taking this 5 volts and I'm doubling it. It's putting out about 8.5, the way I've got it set up here. Then I'm using my circuit that I showed in the previous video about amplifying a square wave. So I'm using the 5-volt square wave to push-pull amplify the 8.5-volt square wave, which I'm feeding into the doubler. So then the actual part that I showed you on the board, I'm feeding that roughly 8.5 volts into my doubler, which is just the 2 diodes and 2 capacitors. And there we have, well, it was at -8, but now I put in a load 1 mega ohm, so it's dropping a bit. But it's going to stabilize. It's starting to. It's probably going to reach like 7.65. Yeah, about 7.69. I'm only using 100 microfarads. This would definitely be better with a little more capacitance, especially on the thing providing the current. But you can see it works. It's getting the extra diode drops, because I had a 5-volt supply that only doubled to about 8.5, and now we're getting about 7.7. But if you use better diodes, you'll get closer. Simple as that. Negative rail. not one transformer in sight. The moral of the story is, if you're only trying to power something very gentle like an op-amp, you can certainly just straight up power the op-amp with this. It's not going to draw barely anything. The timer draws 10 milliamps, so that's not great, but you wouldn't be driving a timer with this. You'd be driving some sort of signal chip, and those are barely going to use anything. So you can take your 5-volt Arduino or whatever, you can pump up and pump down the voltage to run your signal processing system, and then at the output you just bring it back down into the Arduino's voltage range. I have something interesting with an Arduino that I'm going to do with this in an upcoming video. For now, I'll be seeing you.